advance here, let's take a look at these conditions in Fourier transforms. Let's see about the Dirichlet condition. So this is the Dirichlet condition. So the Dirichlet condition is a condition that a signal must possess in order to be able to satisfy Fourier transforms. Okay, so for a signal to be able to satisfy Fourier transform conditions, it must pass through this Dirichlet condition. So the first of the condition is such that the signal should have absolute integral. Okay, so when you say the signal must have absolute integral, then that means if you have the signal in this way, okay, x of t, okay, then the integral of this one, okay, should be, let me bring the t here, should be less than infinity. Okay, so this is what absolute integral. The integral shouldn't be more than or equals to what? Infinity. It should be less than infinity. And then the next condition, okay, so the next condition is that it must have absolute number or finite number of discontinuities, okay, in any time interval. Okay, so it should have finite number of discontinuity in every time interval. So let's say that this is the signal. Okay, so this is the signal. Okay, so in this signal, this is one discontinuity. Okay, there's another discontinuity. There's another what? Discontinuity. So let's say the signal is what? X of t. And here is what? T. Okay, so it should have what? A finite number of what? Discontinuity in every specific time interval. Okay, and the third one is that the signal should have a finite number, okay, a finite number of maxima and minima in every what? Or in every specific time interval. Okay, so signal should have a finite number of maxima and okay minima in every finite time interval. Okay, so these are the three prominent Dirichlet conditions, all right, that a signal must be able to possess, okay, or must be able to satisfy to have Fourier transform. All right, so having known this one, let us move on straight ahead to the properties of Fourier transform. Properties of Fourier transform. Okay, so the first property we shall talk about is linearity. The first property that we shall talk about is linearity. Okay, so what is the linearity property? Okay, so in the linearity property, what it means is that x1 of t, okay, which has a Fourier transform of x1 of omega, okay, and x2 of t, which has a Fourier transform of x2 of omega, okay, then ax1 of t plus bx2 of t should have a Fourier transform, okay, should have a Fourier transform of ax1 of omega plus bx2 of what? Omega. Okay, so this is the first condition, which is a linearity, the first property, which is a linearity what? Property of Fourier transforms. Okay, so now here let us see. So let's see how we can prove this. Okay, so let's see. Fourier transform of what? bx1 of t plus bx2 of t. Okay, so the Fourier transform of this, okay, should be equals to minus infinity to what? Infinity. Okay, ax1 of t plus bx2 of what? T. Okay, into what? E minus j omega what? T dt. Okay, E minus j omega t dt. Okay, so now if you have this one, then what we can do is that we can split it into what? Minus infinity to what? Infinity ax1 of t into what? E minus what? J omega what? T plus what? Minus infinity to what? Infinity bx2 of what? T into minus j omega what? T dt. Okay, so now what you can see from here is that this one denotes what? The Fourier transform. Okay, this is Fourier transform to give you ax1 of omega, and this one is also Fourier transform to give you what? Ax2 of what? Omega. So in this case, you're going to have ax1 of omega plus bx2 of omega. Okay, just as it is required for us. Okay, just as we have over here. So now it is what? Proving. So now it's proving, and we can now write that. We can now write that Fourier transform. Okay, of what? Fourier transform of ax1 of t. Okay, ax1 of t plus bx2 of what? T will give you this. All right. So basically, that is that. Now let's go to the next property. So property number 2. Okay. So property number 2. That is the time shifting. Let's do that one on a new page. Okay. On a new page. Okay. So let's see about the time shifting property. Okay, so 2, time shifting property. So the time shifting property says that if x of t, okay, gives what? Fourier transform of x of what? Omega, then time shifting means that you're going to have x of what? T minus what? T naught. Okay, then it will give you e exponent minus j omega naught what? Omega t naught. Okay, omega t naught. Okay, so this one into x of what? Omega. So now here, let's see how we can actually prove this one. So now what we can do is that we can have f of what? T, Fourier transform of x of what? T minus t naught. Okay, f of t minus t naught is equals to infinity minus infinity. Okay, x t minus what? T naught into what? E minus what? J omega t naught. Okay, t naught. Okay, let's bring the t here. Okay, so now we can say that t minus t naught is equals to what? Tau. So that the t is equals to what? The tau. Okay, so now we can say that minus infinity and then what? Infinity. Okay, x of what? X of tau. X of tau into minus j omega. Okay, here I can have t naught plus tau. Okay, because this one will go here. T naught plus tau. Okay, into what? Into the tau. Okay, into the tau. Okay, so here, before I was having t minus what? T naught, but here it became what? Tau, because of this substitution that I did. Okay, so now if I have that, then what I can say is that I can have, if I should open up my bracket, okay, if I should open up my bracket, then I can have minus what? Infinity to what? Infinity. Okay, x of what? Tau into e minus what? J omega t naught, okay, into what? E, okay, minus what? J omega what? Omega tau, the what? The tau, okay, the tau. Okay, so now I can bring E minus J omega what? T naught out, and then I can have this one, minus infinity to what? Infinity. Okay, x of what? X of tau into what? E minus J omega tau, the what? The tau. That's simple. Okay, so now when you have that one, then you can now say that this one is basically what? Fourier transform, x of what? Omega. So it will give me E minus J omega what? T naught into x of what? Omega. Okay, into x of what? Omega. Okay, so now I can say that x of what? Time shifting t minus what? T naught is what? Is the Fourier transform. Okay, we'll give a Fourier transform of what? E minus J omega what? T naught into x of what? Omega. All right. So now let's see our property number 3. So our property number 3, we can just continue from here. Okay, so property number 3. So property number 3 is the frequency shifting. Okay, is the frequency shifting property. Okay, is a frequency shifting property. Okay. Okay, so the frequency shifting property says that if what? X of what? T has a Fourier transform of x of what? Omega, then E J omega naught T, okay, into what? X of T will give a Fourier transform of what? A Fourier transform of x omega minus what? Omega naught. Alright, so that's what we can have. Okay, so now this means that F what? Fourier transform of E J omega naught what? T into x of what? T, okay, will be equals to integral infinity minus what? Infinity. We just put down the Fourier transform formula. Okay, so before you do that, you put in your x before. So the x here is what? E J omega naught T. Okay, so E J omega naught what? T into what? X of what? T. Okay, and then because it's Fourier transform, I'll have here to minus J omega naught what? T. Okay, sorry, because it's Fourier transform here is J omega T. Okay, minus J omega T. Okay, so here will be E minus J omega T. Okay, so I'll bring the T here. All right. Okay, so now what we're going to do from here is that if I have this one, then what I can do is that I can say that integral minus what? Infinity to what? Infinity. And then I can just deal with the E, because the bases are the same. So that means I can deal with the what? With the exponents. Okay, I can deal with the exponents. So I can bring x of t what? Out. And then I can have E minus what? J. E minus J. If J comes out, that means that I'm going to have if J comes out, that means that I'm going to have omega, and then I'm going to have omega minus omega naught, okay, T, the T, okay. That means that I can have this one. Okay, so now if I have this one, then what it means is that basically if you this one, it shows us that is the what? Fourier transform. Is a Fourier transform. So this one will basically give me x, okay, omega, okay, minus what? Omega naught, okay. All right. So this is the Fourier transform. So this one means that basically is the Fourier transform of what? E j omega naught what? T into x of what? S of what? T. Okay, so this is what? Fourier transform of this one. So here I can say f, and then here I can bring what? T. So that's the Fourier transform. Okay, all right. So that is how you get this one. And then similarly, let's say that you have E minus J omega naught what? T. Omega naught T into what? X of what? T. So that one, you will get a Fourier transform, okay? You will get a Fourier transform of x, okay? This one, you know that here is x, okay? Yes, x. You get x what? Omega plus what? Omega what? Naught, okay? So similarly, it's just like that. All right, so we will continue from the next lecture. Thank you so much.